Hello, I'm Isabella, and I'm going to be talking about my project on simultaneous localization and motion planning using belief space approaches. Robots get information about the world using sensors, but real-world sensors are almost often noisy, as shown with the Intel RealSense depth images here. Thus, an important problem in robotics is motion planning under this uncertainty. One way of addressing this is to perform actions that maximize the information content you get from your sensors. For example, if you're trying to get somewhere in a dark room, you might touch the walls to get information about your environment. So the question is, how can we make robots do something similar? One approach is to make trajectories accounting for the uncertainty of a robot state, or belief space planning. To make the concept of belief spaces concrete, here's an example. This is the distribution of a robot's position in a 2D world updated by a particle filter that takes in haptic information and a robot's velocity. Notice that the distribution is quite non-Gaussian, which is important later. In terms of prior work, a common method for robot localization is the extended Kalman filter, but it's not optimal in systems with nonlinear dynamics. Past work in belief space planning also assumes a Gaussian belief state and maximum likelihood observations. Thus, some questions are, how do we generalize to high-dimensional non-Gaussian states, and how can we make the algorithm filter agnostic? An idea suggested by Platt et al. In their paper Efficient Planning in Non-Gaussian Belief Spaces is to sample from the belief space to approximate it. Here, while the robot is not at the goal, it gets a state with maximum probability, x prime, and samples some other states from the belief space. It then creates a plan maximizing the information difference from x prime and other states, which is an optimization problem solved by quadratic programming. It then executes the plan while tracking the belief state using a histogram filter. If the belief state deviates too far from the trajectory, then we replan. To evaluate this algorithm, I set up an EWA arm facing two boxes of known positions, and we have a laser pointer sensing the distances to the boxes. The only unknown of this system is the position along the y-axis of the robot. And the overall goal is for the robot to localize and reach the goal position, which in this case is the middle of the gap. Applying Platt's algorithm, this is a possible trajectory we get. The robot starts off with its laser pointer at the lower box, so it generates a trajectory that detects a key feature in the environment, which is the gap, and then it goes to the gap. So overall, the algorithm is quite successful with a 93% average task completion rate, and I observed that if it starts closer to the goal, it has a higher chance of success. However, there's still some oddities in the results. If you look at the plot of the trajectory in the previous video, it looks kind of jumpy. And this is because the optimization problem outputs velocity commands that tend to be near zero at the start of the trajectory, so it requires sudden jumps at the end of the trajectory to reach the goal. And also, optimization fails to solve when more constraints on the magnitude of the velocity are added. So further work would be to fine-tune optimization parameters, such as the cost on the joint positions and velocities, and also compare this approach with others such as EKF or other belief space planning approaches, and also implement the simultaneous localization grasping algorithms, or SLAG, in Platt et al.'s paper. Thank you.